Okay guys, this is the last section of Chapter 8, and although Chapter 8 is quite short, it brings all of the things together, so you need all aspects of Chapter 8 to really explain how anything's moving and anything changes its movement. So this is a fundamental chapter. Chapter 7 is also a fundamental idea in physics. Both of those together explain an awful lot. Okay, I'll give you the ideas for the awful lot. So we're going to introduce this idea called impulse, and mathematically it may look very similar to the last stage, but it's not about that. So when we were looking at, for example, the sections to do with Newton's second law, okay, and what was happening during collisions and explosions, all of that showed us what could happen, okay, whether these outcomes from a collision, for example, could occur, and whether there was enough energy to make them occur, to allow them to occur, okay, but it was all to do with whether they had that enough oomph, technically speaking, as they went through. So what is that oomph? It's impulse. So during the actual process, we haven't considered. We've looked at what we've got before, we've looked at what we got afterwards, or could have afterwards, but we haven't actually said, for example, in the explosion section, what is happening during the explosion. Okay, and that really is what we mean by impulse. Okay, so according to the basic theories of force and acceleration and so on, a ball comes in, it has a certain mass, it hits a wall, for example, and bounces off. Job done, there's a force due to the wall. But of course the force changes. And when you're looking at things like collision panels in cars, crash mats, our bungee jumper, hoping that the bungee is elastic enough, then we need to think about whether the impulse is high or low, and that's what gives us detail. Okay, so section 5 is really what is happening during the collision, what is happening during the explosion. Okay, in other words, what's actually making it happen. So all the ideas to do with forces and Newton's second law, okay, which is of course based on the other two, forces external to the process make things happen. But yeah, if we have some sort of collision going on, then that external force where the ball hits the wall, the force from the wall is causing something to happen. But how it does it, whether it hurts or not, whether the thing that smacks into the wall is going to get shock loaded or not, all depends on this thing. So let's go for a bungee jump a second. There is a maximum loading on the human spine for British standards, for European standards, CE certification as it's known. This means that you should have a maximum, I should say, force is less than or equal to 6 kilonewtons. Okay, 6,000 newtons is enough to deform the spine if it's pulled at different angles, etc. So everything has to be related to that. Well, the falling person may, when they're hanging, certainly not be 600 kilograms or 610 kilograms if you want to do the conversion. They're actually going to be a lot less than that. Okay, but depending on how hard the collision is, you can create much bigger forces. Okay, so this is the reason why you need collision zones in vehicles and things like that, to make your collision, shall we say, soft enough. So the maths of it is really important. The section in the notes is actually quite short, but we'll pick up on some of the details in a second. So let's just wipe that board. And what we're going to look at is this idea of what we mean by impulse. So my first head of physics that I worked for many years ago, early 90s, he would not fly in aircraft because of this. Now, I've got a statistical basis and I use my risk assessments to analyse. Yeah, there may be things like impulse, but statistically it's safe to fly. But it is a very important idea. Whether a bird striking an aeroplane could break blades or not depends on the property of the blades that we have chosen in your motor, okay, in your engine. Now, a little bit of a hint. It has a useful unit, Newton seconds, so you can probably already half guess on what's going on, but we'll give you the notes. Okay, so if we look up here, we'll just fill in that top section. Basically, where we were with the useful form of Newton's second law was that we get our final velocity, subtract from that our initial velocity, and we'll divide it by the time it takes. Okay, now all we're doing is rearranging that slightly to give us impulse. So impulse is F delta T. Okay, that simple idea there is what's known as impulse. Okay, so units, newtons, seconds. Now, what the impulse does is the other side of the equation. So these are two different things. It's a bit like saying acceleration of gravity equals g. It doesn't. It equals the same size of g, but they're two different ideas. One's a field strength, one's an acceleration. So here, the impulse equals the change in velocity. Sorry, the change in momentum, correction. Okay, so if we have the ball that's coming in and going to hit the wall, it has a certain speed, okay, beforehand. It bounces off with a certain speed. The difference in those is what produces the size of the force. So that comes from the change in momentum. Now, just give you a little heads up, units wise they are different, so that kind of gives you that bit of hint. So this is kilogram meters per second, whereas this is Newton seconds. Okay, so that kind of fact that they're in different units, although they're equivalent units, they're different, so they mean different things. So this is to do with force, but it is not a force, it's what's happening to the force over time. It's that change in force. Okay, and that's where the crucial difference is. Now I should say an impulse, for example, if you were to kick a ball, the impulse that you impart, that you give the ball, will change its momentum. So this works two ways. Okay, if you've got moving objects, it will have some momentum, there'll be a collision, and that collision will change the momentum in that object and in something else. So it will change the whole process. So process, effect, before and after, okay, during. That's probably the way to think of it. So that for us is during the collision. Kicking a ball is a collision, for example, or explosion. Whatever that event is. Sorry, I can't spell explosion while talking. Okay, whereas that is before versus after. Okay, so that's your comparison of what's happened, but this is what it's happening during it. So, summed up as that crucial idea. The impulse is what changes the momentum of a thing, for example, a ball. Now, let's just take an example. Okay, we're going to stick with a ball. We're going to drop a ball. Now, the ball, we've got a pair of them. They're matching. They're falling onto two different surfaces. Okay. Now, let's presume these are a hard ball, so a steel ball, for example. They will fall onto two completely different surfaces. Say this one's softer. Okay. What happens is that, for example, your billiard ball, snooker ball, pool ball, if you drop it, it's actually quite bouncy on a surface that has a very hard response. Okay, so this, what you'll notice is that it bounces off really quickly. This is incredibly small. So what it means is that is really big. Okay, for a certain size change in momentum. If we were to drop something onto a softer surface, then what you'll find is, again, assuming it bounces up the same, so again, delta mv on both of them is the same, okay, then what happens is our impulse will change. So our impulse will still be the same, but how it looks is coming back down to, again, our two parts. So, okay, so what I've got going on, ball bouncing back and so on. Sorry, I just had an interruption flowing through. Yeah, this, if it's softer, will have a smaller, a larger time. It'll cushion it and push back. So that will be bigger, in which case the force will be smaller. Now, normally we tend to think of not the surface, but again, if you were to fall onto a hard gravel or tarmac surface off the top of a swing, for example, like we had in the old days, you'd get a really big force on you. There'd be a lot of broken bones. Kids, when they were my age, when I was at school, lots used to end up in hospital falling off playground rides and things. Nowadays they have a squashy surface which increases the time, so you've got a smaller force. Still the same change in momentum, but the collision is different. Okay? Now, if we were to change that, then there's another way of looking at it. If we had something that bounced and bounced back up, okay, that's big, and something that just stopped, so splat, that was it, then, assuming it was the same momentum at the beginning, mv and mv, what you'd find is, of course, we've got a bigger change in momentum there than we do here. So not only do we have to stop the ball, but we also have to push it back. So we've actually got twice the change in momentum. What do I mean? Well, here, if I'm going to go at the beginning, I've got mu, excuse me, that's terrible u, try that one, and it comes out at mv. Well, mv minus mu, assuming that they are the same momentum, they are the same velocity, then what I've got is that one's going down, so that's going to be negative. So what I end up with is mv minus negative mu, which is the same size, so I'll just conveniently change that to v, which equals 2mv. So that, compared to just that becoming 0, is twice the change in momentum, so I will produce twice the force to make it bounce. Okay, so that's telling me what the collision is like because of the effect I can see from the bouncing or not bouncing object. So if we have a total inelastic collision, so all the kinetic energy disappears, it needs a big force. Okay, so it all links together with Chapter 7 as well. Right guys, so that's kind of summed up there, as I hinted at last lesson, okay? And it also gives us the idea, as I said there, commonly used in sports, why they tend to follow through with things. So if you are pushing a ball for much longer time, then what you'll get is you'll need less force to change its speed, or for the same force, you get a bigger change in momentum. Okay, so there's two ways of looking at those. Now, in terms of how this will look, it comes from the idea of what happens with force over time. So impulse is the area, okay? And fairly commonly what they'll ask for is, they'll give you a shape. These are very false shapes, I should say. Maybe a steel ball hitting a steel surface would do that. Suddenly there's a force and then suddenly there isn't. Building up, force increasing during the collision and reducing. In reality, it is more likely to squash a little bit. The force peaks at maximum squashiness. So again, from the videos I show in my PowerPoint, you can slow motion collisions, you can see a ball squashing, squashing, squashing. Hooke's law, maximum compression, maximum force, and then it releases again. So you often get quite a symmetrical curve. Okay, and if they ask you for the impulse, which is usually step 1 from a graph, then you will find the area underneath the graph, which then gives you that change in momentum. Okay, so how will we do this? Well, again, you can use your trapeziums, etc., etc. What I tend to do is take about that bit less then, excuse me, there. I'm going to go to the peak value, and again I'm going to find that halfway point. Okay, so again I would show this nice and clearly. That's a little bit too far left. It should really cross there, so my area will be wrong, but I can do it all in one go. Okay, so that whole idea is that those are equal areas. So if you've got a nice symmetrical graph, it's fairly easy to do. Better than I have, take a bit of time on it. Okay, so what we've got here, so I'm going to label up this little bit of graph here, but this area gives us this. So the idea for questions: find impulse from area. I'm just going to keep this over here because I want to write over on the right. From the area, then that equals the change in momentum, and if you know the original or final velocity, you can get the other one from it. Okay, so that's the process with that. In terms of the graph, again, this more realistic one is giving you the best bit. Here you've got your idea of a low force or a small force, and why, as the object starts to crumble, starts to crumple, sorry, not crumble, to squash, let's put that. So where it just starts to make contact, that's where you feel your force. As it squashes more and more, that's fine. And then here we've got max compression. In other words, force is proportional, well, let's give the equation, equals kx from Hooke's law. So maximum compression, maximum force. Okay, and that's the idea. So how things collide, the shape of this tells us all about the safety factors. So the main idea of impulse is really about, firstly, have you got a large enough force to stop something or start something moving? What's the effect of it? So sports tend to worry about that, but a lot of the stuff like sports body armour, collisions in cars and so on, it's about creating basically as wide an area as possible, because that will give you the same area for a smaller force. So the wider this is, the smaller the peak force will be, and that is good to protect you.